In this video, I am going to prove that the limit as x approaches 0 of sine of x over x is 1. I like this proof very much because it doesn't use any complicated mathematics. It's just some high school geometry and trigonometry. We will begin by drawing some pictures and getting information from them about the function sine. I draw a circle, and it's going to be the unit circle, so the radius of the circle is 1. And on it, I'm going to draw a radius that forms an angle x from the positive horizontal axis in the counterclockwise direction. And I'm going to call A the point where it intersects the circle, and draw a vertical line from it to the horizontal axis that intersects at B. Since the radius of the circle is 1, the coordinates of A are going to be sine of x and cosine of x, or specifically, this vertical distance from A to B is sine of x, and this horizontal distance from O to B is cosine of x. And this is true because the radius of the circle is 1. Actually, this is what I consider the best way to define sine and cosine. But perhaps you have used or seen a different definition, and in that case, if you need it, pause the video for a moment and persuade yourself that this is true. I'm going to draw another vertical line, this one from the rightmost point of the circle. And in this picture, now the distance between C and D is the value of the tangent of x. And this is true by looking at the triangle OCD. Again, if you need it, pause the video for a moment and convince yourself. And this is all the trigonometry we are going to need. We're going to get everything from this picture. So I will just skip this part of the picture, and what I will do next is compare the areas of 3 different regions. The triangle OAB, the sector OAB, and the triangle OCD. Let's do them one at a time. First, the smaller triangle OAB. We know that the area of a triangle is 1/2 of base times height. So in this case, the area is 1/2 of cosine of x times sine of x. Next, let's look at the big triangle. Again, the area is 1/2 of base times height. In this case, the base is 1 because that was the radius of the circle, and the height is tangent of x. And finally, let's look at the sector. Perhaps you know the formula for the area of a sector, but in case you don't, here's how we would obtain it. I have drawn a sector with internal angle x and radius r. So the angle is x, and I want to calculate the area. Let's call it S for surface. The key fact to observe is that if I double the angle, then I will be doubling the area. If I multiply the angle by a factor, I will multiply the area by the same factor. So I'm going to compare this sector with one whose area I know, specifically the full circle. For the full circle, the angle is 2 pi, and the area is pi r squared. And now I can simply use proportionality to obtain an equation from which I can calculate S. I can say that x divided by 2 pi must be the surface S divided by pi r squared. So from there, and we get that the area of a sector is 1/2 of the angle x times the radius r squared. So let's use this formula back in our previous problem. I was trying to calculate the area of this sector. In this case, the angle is x, and the radius is 1. So the area of the sector is simply 1/2 of x. And I've obtained 2 inequalities, and I will continue from there. I can now forget the picture, keep these 2 inequalities. I'm going to multiply everything by 2. And so I have that cosine x sine x is less than or equal than x is less than or equal than tangent of x. And I'm trying to obtain the information I need from these inequalities. First, I will write tangent as sine of x divided by cosine of x. And next, remember my ultimate goal was to compute the limit or a limit of sine of x over x. So let's divide everything by x, so I obtain sine of x over x somewhere in the inequalities. Next, to get some information about sine x over x, I notice that it appears in the first inequality. So from the first inequality, I can say that sine x over x is less than or equal than 1 over cosine x. I also notice that it appears in the second inequality. So from the second inequality, I can say that it is greater or equal than cosine x. And now these 2 inequalities contain the function sine of x over x, so I'm almost done. Notice first that these inequalities are true for any non-zero value of x. Strictly speaking, I've only derived them for positive x. The picture was only for positive x. But we can do a very similar argument and justify why they work for negative x. They don't work for 0 because I'm dividing by x, so it's not allowed to have x equals 0. Now, the function I care about, sine of x over x, is now sandwiched between two other functions, cosine x and 1 over cosine x. And those two functions are continuous and well-defined at 0. Specifically, the limit at 0 of cosine x is 1, and the limit of 1 over cosine x is also 1. And from here, I'm basically done. I have a function sandwiched between two functions whose limits I know, and I want to compute the limit of the function in the middle. Well, here's the graph of cosine x, here's the graph of 1 over cosine x, and the function I care about is squeezed in between them, so it needs to have the same limit. Or in other words, I'm using the squeeze theorem to conclude that the limit as x approaches 0 of sine of x over x must also be 1. And that completes the proof.